My name is Matthew Waddington. I'm a beekeeper in the Snoqualmie Valley east of Seattle, the Cascade Foothills. 2021 is going to be my 27th year of beekeeping here. All those years have been with Varroa. And being that it's January, I thought it'd be a good time to spend some time with Randy Oliver's excellent spreadsheet. And what you see here is a variation of the graphical portion of that spreadsheet to present the information in a slightly different way. And what I want to do with that is perform some experiments and some animations that help to determine what the most efficient treatment timing of high efficacy treatments might be. And I want to do that in 4 different experiments, and I want to show you really quickly first off what the outputs and inputs are for those people that have not seen the spreadsheet before or this variation of it, and then I'll get right into the experiments. These are the inputs that Randy has in his spreadsheet. First off, these ones here are the most important. D represents the letter represents the type of colony. There's a number of selections you can make. Those are all editable, or you can check them out on the colony tab of his spreadsheet at the bottom of the page. 25 represents the number of initial mites you might expect for your hives. This is a number representing migration rate from the hives, and goes from 0 to 4, also on the colony tab if you want to take a look at it. The other input that's primary is this column here, which represents the efficacy when you're treating it and within that 2-week period. They're approximately 2-week periods. They're all 26 divided into 365 days. This is an extra one that I've selected, included, which is an OAV treatment of this efficacy, which is editable just in the spreadsheet. I found it interesting. It's certainly not going to radically change anything, but it's an interesting addition to see how that actually affects things. So when we want to add information to those particular inputs, we just type in the number that we want to use. So let's say I want to add a 90% efficacy treatment right there. One thing I did add is a green bar to the chart, which shows you where that treatment occurs. So when you're just looking at the chart itself and not paying attention to what values you're putting in, you're seeing the values appear as green bars. The other thing I've done is, in terms of that OAV, is if you enter an X into this column at any particular 2-week period, remember this is just a single treatment of oxalic acid, so really only affects the phoretic mites. You enter an X, and what it does is take the number 90%, at whichever you want to assume, you can make it less or greater, multiplies it times the number of phoretic mites that are in that period, and then gives you a phoretic mite kill. So it shows up right here as a number, which you can just see down there. So in this case, there were 19 mites. It applied 90% to them, killed 17, and changed everything downstream to affect that. So those are the primary inputs. So these are the outputs that you'll see in this chart. First, I want to explain that this is on the left-hand side is the left axis, y-axis, is a logarithmic scale, which I think allows a little bit more room to show what happens to these numbers, the lesser valued numbers, as your treatments progress. In terms of the graph itself and chart itself, you'll see that this is the adult bee population. This is the capped brood population. And this is the capped brood infested population. Of the first 2, those are not affected by your treatment plans. Those are all driven by the colony tab at the bottom of Randy's spreadsheet. It's important to check that tab and to check the assumptions made. In this case, I'm starting with a D value, which he's made some assumptions for, and it's important to go through and make sure that actually correlates to what you're seeing in the field in terms of numbers of frames of bees. And that's but it's purely driven by that. So it's pretty much background. This value, however, is very much driven by how you start treating. So we'll look at that. The lines, this last line here is the tilt, meaning if you exceed 30%, here that shows up automatically. And it's just saying your hive will not survive. The 30% is a number that Randy has incorporated in the spreadsheet, I assume based on experience and science, so that just shows up automatically. The lines that I've showed here are pretty much the same as Randy's, but a little bit different. This one here is just a number correlating to the total number of mites that are in the hive during that period. This blue line here I've included is not something he has, but I thought it was important, which is the phoretic mites that are in the hive at that particular time, and also are similar to the mite drop you would expect if you treated at any particular time at a high efficacy with phoretic mites, like with oxalic acid. This is related purely to whatever selection you made here and represents the number of mites coming in on other on robbing bees, or your bees bringing in mites for that period. So 103 mites come in during that particular period, etc. This is the last line here is a line I introduced, which is the percentage of infested brood. So at this point, 30%, that's that number we're worried about up there, right? So it exceeds up there, it's going to crash. At this point, 14% of the brood is infested, et cetera, et cetera. We're trying to keep that as low as possible, so it's an important number. That is pretty much the main lines that were involved. Up on top, we'll see a couple things here, which I think are I sort of randomly, not randomly, but I think are these the most important things to consider. That is the maximum mite population that you'll see throughout the year. This is probably the most important one, which is the maximum brood infestation. And this is the end of your mite count. Maximum brood infestation very much relates to whether the hive crashes or not, and in particular in times such as the formation of winter bees, you want to keep very low. So probably the most critical number, I think, in the three. The maximum mite population is important to keep low. How important it is, if you can keep this down as well, I'm not sure, but obviously those kind of work in tandem together. The end of your mite count is only important in that you want it to not exceed by very much or be close to that number there. Obviously, in this case, it's considerably off, and that would not be a sustainable treatment plan, even if this red bar didn't show. So you want to make sure that those two are similar. If they're not similar, you just can take that number, or they're similar but not too far off. You can take that number, put it in there, and see how it goes. And if it still works, then it's potentially a sustainable treatment plan. So that's pretty much all the outputs that we're seeing. So to determine which treatment plan is successful, there's obviously a few things that have to happen here. One is we definitely want to have this number, I was saying, as low as possible. And if we can then secondarily, if we had two equal values there, we certainly want to have that one be the lower of those two values. We want to look at the end of year mite count and to make sure it doesn't exceed that value. And the other things we want to do is consider where those treatments happen and which bees are being benefited by the treatment plan. So particularly if we're talking about winter survival, we want to start thinking about, like, does that happen in months where winter bees might be formed, and making sure that numbers such as brood infestation are low there, and keeping our viral loads seems to be also a component of deciding which treatment plan is important. So that's the main thing I'll be looking for as I proceed in these experiments, is trying to determine which treatment plan is successful. I should add the other thing is making sure that whatever treatment I'm talking about using or thinking about using is works with the honey, the nectar flow at the time. So for example, for my area, working these months and having a primary treatment that's not approved for use with supers would be a problem, because that's all our honey particularly draw for blackberry. Other ones are included as well. So just looking at that as well and making sure that that corresponds to whatever treatment we're planning is important. I have 4 experiments to share, and these are the result of trying to determine what would be a good way to actually determine which treatment times would be best. So I designed 4 of them. Experiment 1, I assume that there's only one treatment available, and I can do that anytime, during the year. And so I go from January all the way through December, applying that treatment, a high efficacy treatment, and try to determine which one is the most effective. Again, assuming I only had one available. Experiment 2 is looking at a second treatment, assuming that first one didn't take care of the problem. I use that as a base, and then apply a second treatment and go again from January all the way through December, applying that second treatment and finding out which of those combinations is the most effective. Experiment 3 is assuming a third treatment, assuming that the first two weren't sufficient, which they are not, then going through and finding out, okay, what's the third treatment possibility. Experiment 4. That was actually then going and tweaking the different options and saying, okay, now that I've figured out which 3 might be the best in terms of the model, are there ways I could tweak this? I can move particular treatment times to different times or different types of treatment that would make the whole treatment process or the whole treatment program more effective. So that's the 4 experiments, and that's what I will share with you now in the different animations. Experiment 1, single 90% efficacy treatment with moderate mite migration. So I'm going to take a 90% efficacy treatment and apply it every 2-week period throughout the year and see how the brood infestation and mite population reacts, and you'll see that as it moves through how those numbers are affected. That was January, it dropped it way down. Going through spring, February, March, not a lot of reaction downstream, but you'll see, of course, an immediate reaction just adjacent to the actual treatment time. Now we're seeing some change, 47% to the infestation, 46%, 44%, so seeming to drop, 36%, 30%, 24%, 19%, and then back up to 33%, 77%, and that continues on as the hive has died. So in that demonstration, I think the obvious lowest brood infestation was that 19%. So let's go back to that. Back up here a little bit. 19%. That's on September 15th. Now it's not the lowest maximum. It's not the lowest of the maximum mite populations, but it's the lowest of the brood infestation. It seems like a very good candidate to me because it also drops the infestation rate in the potential winter bees to its lowest potential. The other choice it would be to go with the maximum mite population and keep that down. Let's see where that would be, just as a comparison. Right there, I think. So August 1st. So let's take a look at one more graph that represents this, but I think the choice here is 19%. So another way to represent that is with the just a graphing out of all those possibilities. Let me show you really quickly an example of that. So in this graph here, I've just selected manually written down that data from the previous exercise, and I'm showing it in a slightly different format. So pick any particular day, let's say period, May 1st. So what I'm just showing there is that on May, if you treat it in May 1st, your end of year mite count, that's the yellow, would be in the range of 2,000. And also in this case, because the blue line's echoing that, the maximum mite population would also be 2,000 if you chose that date. Your maximum brood infestation would be this percentage over here, close to 50% if you chose that date. So if you were going for lowest brood infestation, you would choose that date, which is, as we just indicated, September 15th. If you're choosing lowest end of year mite count in this particular scenario, you would choose one of those. And of course, if you're choosing lowest maximum brood population, that would be the date. So they're not all the same. I mean, these ones are close. But again, I think the most important date here is that particular one here, the maximum brood infestation, particularly since it works so well with the end of year. So next step is to say we're going to pick that date, and let's try an experiment 2 where we go through and try to figure out its best timing to work with this particular timing. Experiment 2, two 90% treatments, one of them being on September 15th. with moderate migration. So you see the 9/15, the September 15th treatment established for the best of the single treatments and with its values above. Now we're going to go down methodically through each of the two-week periods with the second treatment and see how that affects the numbers. So again, we're looking for the best of show on a second treatment. So beginning in January. Again, that initial drop, which seems so important, but it has little effect on the end results. The first one does, but the other ones don't. These spring ones move things around in their space, but not downstream. So now we start getting into some changes here. 12%, 11%, that's a good improvement. 11%, 11%, 10% even, 9%, there we go. Oh, back up to 14%. That's not a counting one because it's doubled up. 16%, 17%, 19%. And then that's bottoms out. Okay. So I think our best shot of that one, if I'm going to go scroll back here, was right here at 9%. That's the best one. It's got a 1,981 maximum mite population, end of year mite count of 218, still high. The maximum mite population is lowest here. So if we were thinking that was the most important thing, we would treat earlier, but we would suffer a little bit from a higher infestation rate later. So arguably, maybe it's somewhere in between these two. But for the purpose of this experiment, trying to really maximize it, I'm going to go with this 8/15, the September 15th treatment. So treatments that are possibly 2 weeks apart or so, 2-3 weeks apart, in the end after the summer is over, or middle of summer, I guess, 8/15 to 9/15, and those seem to be the winners in this particular scenario. So now we're going to go to 3 treatments and see how that pans out. So this is experiment 3. We've established 2 treatments, one on 8/15 and one on 9/15, that seem to give the best mite kill and lowest brood infestation of any of the other possibilities. So now we're going to try a third treatment and see how that works. Obviously, we're at a survival point here, but not necessarily with the end of year mite count. But we are seeing a pretty good drop in the infested bees at the end of the year. But let's watch what happens and see if we can improve that with a third treatment. So here we go again, going from January to December, one at a time. There's January. That's our initial drop. That already drops us to 9%, which is nice. The 9% stays constant as we move through spring. Doesn't seem to have much of an effect at all on what we're doing. It definitely keeps our mite population down. Now our mite population is increasing. We're at 8%, and not seeing a big dramatic change. And a year mite count, of course, drops significantly as we start applying those high efficacy treatments to just the phoretic mites. So that's a debatable question. I think this is a good point to look at. What is the best treatment? In kind of going through this a couple times on my own, I think that even though we see 8 and 9, 8 is lowest, it really isn't necessarily the most effective if we can actually get a mite count down to, like, this is the lowest mite count. So I would argue that being at 9% there in 421 mites versus, say, 8% there and 1,400 mites, that this is a significantly better time if we had to add if we wanted to add a third treatment. So with that mode of investigating here, with 3 treatments, just going through that process, this is the front runner, I think. A treatment in the early part of June, a treatment in mid-September, and a treatment mid-August, and a treatment in mid-September brings our numbers pretty low. Now the question is this the best of the best? Is there another way to rearrange that? And that's what our experiment 4 is going to look at. So let's look at that now. Is is tweaking these numbers to see if there's some places that these could be shifted slightly that would make an improvement on our numbers up here. So to start with, let's just record the values that we have right now that are were the best of the solutions that we found in those previous 3 experiments. So an 8% and a 208 end of year mite count. Now, one obvious thing I'm sure has occurred to anybody watching this is that we're not doing the obvious thing of treating in January or in the fall time to try to reduce the numbers, and that's an easy way to eliminate that. So that's a kind of a no-brainer. I'm going to go pick my November 15th time and just drop some oxalic acid or a low, phoretic mite, high efficacy for phoretic mites treatment there, and you'll see that number drop pretty quickly to 0. You just bring that through. Now, that might be a little bit overstating the case, but that seems really an easy thing to do. The other one would be in January, of course. But before I do that, let's look at some other effects here. One thing I noticed was if I move these down 2 weeks. So actually, let me write the numbers down. I'm sorry. Go back up here, reestablish that, and write these numbers down. So now we're down at a pretty high population. But we were at 8%. Oh, same thing, 8%. Same thing, 5, 6, 7, 7. Yeah, okay, that's all good. Sorry. I'm going to move these down to these positions here. And see what happens when see what happens there. So I just moved them 2 weeks, kept them 2 weeks apart, moved them down. So that's kind of interesting. All of a sudden, the maximum brood infestation goes down to 4%. We could get down that low by just moving those out of that range. And I think what's going on, of course, is that we're moving into this territory here where there's much less capped brood, but it's not quite meeting the same curve dropping as the infected brood, and so you're seeing a dramatic increase in it. And that may be to our advantage if, in fact, we're trying to reduce the infected amount of brood in this last remaining part, which are creating winter bees. So it may be that that's a good move. The other thing I would like to do is eliminate one of these treatments, and it seems like a lot. So I'm curious about this one. This is a bad time to treat. In fact, almost an impossible time to treat in the Pacific Northwest if you're using anything that can't be used on supers. That's right in the midst of our blackberry season. So I'm wondering, can I do something different here? And obviously the one thing that I can do differently here, so right now we're at 667, is eliminate that treatment and see what happens if I just confined it to an earlier January treatment. Let me just put an oxalic acid treatment in the beginning of January. In the beginning of January. And see what happens here. So our curve comes up. So whether this is an anomaly of the spreadsheet or because it affects somehow differently, I don't know. But for some reason, that actually reduced, or limiting that treatment, adding that treatment was better, and has now reduced our population to 505. So this is looking pretty darn good. This is a sustainable treatment program in this regard. I mean, 505, 4%, 208. If this is at all echoing reality, which is arguable, I feel like I already do this in some ways, but and not seeing this kind of thing. But in terms of the model, this seems like the top runner. Again, these could be tweaked even further and played with. One of the things you'll notice right off the bat is that reducing, I won't go through this, but reducing these percentages, well, if you reduce this percentage to, let's say, 50% efficacy and 50% efficacy, some pretty bad percentages. Let's just see what happens. There's a number at which it still retains, right? So it just reduced the efficacy of those two treatments. I think it does. It might still be computing. Right. Considerably. And we still don't see a crash. We see a high brood infestation of 17%. But not 30%. So the efficacy seems a little less critical than the timing. That seemed like an interesting point. The other thing that happens is that if we say this is not, I'm wondering if, let's say I'm not living in a two world, I'm living in a 4 world, what happens? And so let me jump that up and see what changes here. If we jump up the mite population. So kind of understandably, the mite population goes radically up, and this goes up to 8%. This still stays 0 just because we're doing a giant treatment at the end, or a significant treatment. But that's real significant. There's not a giant jump, it's still survivable. So in effect, this does seem to me to be a pretty good suggestion of a model to be used that seems to, it certainly works with the computer model. Um, Whether it's real or not and can be used, that's another question. But I think this is kind of the front runner. So lastly, to summarize, a few observations, not definitive ones, and certainly not the only way they could be interpreted. But here's some of the things after going through that exercise that I think that are important. Whether or not they apply to the real world and actually treating hives, I don't know, but certainly they apply to working with this model and looking at ways to keep the numbers down within the model. So observation one is that paired treatments, 2 to 4 weeks apart after August sometime, seem to be the most effective. This most effective pair of treatments that can be done are at that time. Observation two is that timing is important. That small shifts in those two treatments, moving around a little bit, can actually have a significant effect. Having or the maximum brood infestation, for example, that it matters how far apart they are. Observation three is that having a broodless treatment broodless treatment in the winter months is super important and really augments in a super effective way any other treatments that are being done. It's not the most important treatment that can be done, but it certainly accelerates the effectiveness of the other treatments. Observation three is that spring treatments don't seem to have, at least in the model, much of effect. There might be other reasons to do them, keeping viral loads down or such, but in terms of their effect on the larger populations later on in the year, particularly with a migration load, that they don't seem to be that important. And so I think that those could be not even done, and everything would seem fine. Except, this is in the model again, but that seems definitive. Observation five is that timing might be more important than efficacy. So just playing around a little bit with switching efficacy on the treatments really had much lesser of an effect on hive survival than the timing had on hive survival. So that seems like a clear observation that seems true. So those are my takeaways, and I'm going to think about whether or not this can apply to this coming year's treatment plan, and if it can emulate, if I can better emulate what actually I have seen in the field with the hives I have. So that's my next goal. But I hope this has been helpful to you and interesting, at least. If those of you have stuck with the video, you certainly encourage you to work with Randy Oliver's treatment spreadsheet and play with it around and see if you find out any other observations. I'd be sure interested. So good luck beekeeping this year. Thanks for watching.